Hello, everybody. Welcome to the Axelar Learn session. Today, we're going to take a look at our cross-chain NFT example, and basically, it is built on top of general message passing protocol, and what it allows you is to create contracts across different chains that will allow you to send NFTs cross-chain. So my name is Kiryl, and I'm co-hosting today with Canh, and Canh is going to show us his screen, his development environment, and explain how to send NFTs cross-chain in further details.
Yeah, hey everyone. And the specific repo that we're going to be looking at is this one here. I'll provide a link for that in our collective chat. So I'm gonna run through this, and if you guys would like to follow along in your own on your own screens, you're certainly welcome to do so. I think I might have done that right, but Kiryl and Eli, if you want to help make sure that that gets propagated to the rest of the channel, that would be great as well. So actually, right, I'm gonna try to run this from scratch, right? So I'm literally going to pull the repo and start the scripts again from scratch. So let's go ahead and clone this. Oh. Let's clone this into my local machine. And then I'm going to CD into it and get it going in my code editor. Yeah, so the specific example that we're going to run is, in this example, is a web repo, and the example is NFT linker. So just opening that up in my Visual Studio Code. I'm going to start this going and then just give some context of what we're going to do here. So if we go to the README, the initial setup scripts is to create an environment file, a .env file, where you'll declare things like, and this is totally just testnet. So feel free to use this key here that is generally funded across each of our accounts, but these are certain environment variables that we set and instantiate for the app. So let me, in parallel, open my terminal. I'm going to have a couple of going, just because on one instance, we're going to power our local environment, and then on the other, we're going to actually be running the scripts that's relevant for this repo. So let me start with a clear screen. All right, so if we go to the README now, the very first thing that we want to do is create that .env file. So you just copy that script here, and you see I will have created this .env file. And the next step is to run yarn, which installs all of our dependencies for this project. Okay, so while that's going, I'm going to give that a second. This sample demo is just another in a series of demos that we've done in the past, right? To show different use cases of general message passing. Now, what we're going to do here, like what Kiryl mentioned, is transfer an NFT that we have minted on a source chain into a smart contract on a destination chain. And the building blocks that we're going to use that is one of our methods within our GMP protocol called call contract, right? So nothing in this, there's nothing in this where Axelar would actually care that we're dealing specifically with an ERC 721. The ERC 721, which is the standard for this NFT that we're using today, is going to be built into the helper contracts that we're going to deploy, and we'll do the code walkthrough for that, as opposed to something that's inherently innate to Axelar itself, right? So with that stage set, you see that our package was installed. The next step is to actually go ahead and power our local dev environment. What that means is, our local dev environment, we take all of the EVM chains that we support, and we actually create a local instance of that for each EVM chain And we run it on locally hosted RPC or RPC endpoints. And to simulate the cross-chain functionality, we actually run a simulated relay function on a cron basis, right? So you're actually able to then develop your smart contracts on all of these, develop and deploy all of these smart contracts on these chains. And as you're making that call contract invocation, you're going to be using that simulated relay function. So let's go ahead and instantiate that. And it is a simple start script here that I'll just copy into my second terminal.
All right, yeah. So what it does essentially, it creates for 5 different chains that we are simulating here, it creates 5 different instances of Ganache, and they are exposed via RPCs. So basically, essentially, if you're developing cross-chain applications, you can have several chains simulated in your local environment that allows you to move and experiment quickly.
Yeah, and you see here there's some noise here that may or may not mean anything to you, but these are some infrastructure contracts that we have deployed on all of our EVM chains from Axelar. So you see that this has what we call a const address deployer. This is a utility contract that we use. We have our primary gateway contract, which acts as the router between that EVM chain in question and all of the other chains that we support. And we have this gas receiver, which is another support contract. And I don't see it here, but I think we will have the option of deploying a stub fake stable coin for local testing purposes as well. But the point is, as soon as you run this local dev environment, these infrastructure contracts are all kind of set up for you. So now the next step is to actually build the contracts that we've written here locally. And I'll show you in this repo where those contracts are actually written. They're actually in this contracts folder. And you see that there are a couple of contracts here. So starting with the first one, this is just a sample implementation of an ERC 721 contract using some of the interfaces that are exposed through OpenZeppelin, right? So this has a couple of different methods that can be called externally. One is a simple mint of a contract, and the other is minting with metadata, right? So, and then we get to the NFT linker. So this NFT linker is one that, and both of these contracts we're going to deploy in all of our chains, or each of the supported chains that we're doing in this demo, right? So this NFT linker, you'll notice that it takes the form Axelar executable, and that is actually really important, right? For these contracts, as you're invoking from chain A to chain B, they all have internal methods that will be called when the contract is the destination chain. So if I am initiating a call contract invocation from a source chain A, and I'm declaring what my destination smart contract on source chain B to receive that message would be. Once that smart contract receives that, it actually invokes an internal method called execute for the call contract invocation, and that execute function, you would view that basically as a callback. It tells your destination chain or the smart contract on your destination chain what to do once that message is received. So and that's built into this Axelar executable contract here, and the execute method is at the very bottom. You see here that what this is saying is, yeah, once we get the payload, do some internal logic, decode the payload that comes in, and then do the custom logic that we declare, right? So that is that is the code that gets executed when this NFT linker receives it as a destination chain. But in the same contract, you could also invoke methods, or you could also write methods that you can invoke there from a source chain. And the one that we're going to do today is a method called send NFT. And there's some if-else logic here. What we're doing is we're saying, first we're saying if we're dealing with a deployed ERC20 token and we want to transfer that to a destination chain, one that already exists on that home chain, then simply send it. And there's an internal method that we've written here, which you can go through. Otherwise, if that is not the case, then you're dealing with a token that actually natively exists on on some other destination chain that you will have minted in this contract, right? So this if else kind of accommodates that for you. So high level, that is what the contracts do. So let's go ahead and compile those. And we can do that with this build script.
That's right. That's right. So just to recap this, this contract is inheriting both Axelar executable and ERC20. And this contract can be called cross-chain, and also this contract to be called directly on-chain, so it can send something to a different chain. So it is kind of like a cross-chain NFT linker hub and NFT implementation in one package.
Right. So now that the contracts are built, we see that that was built successfully. Now we can go ahead and deploy these contracts, right? And by the way, for all of these scripts that we're running here, these are actually NPM scripts that we've written into this repo as well. So if you go into the package JSON, you can see the actual scripts that that are being run under the hood. So for this deploy script, for example, you could go into the scripts directory, go into the deploy contracts file and see what's actually happening, see where you're deploying which contract to where. So let's go ahead and run the deploy script, which we're going to do against our local dev environment. All right, so what you see here is that on each of Avalanche and Moonbeam, and we've only used these two EVM chains because that's what we're doing in our demo, but in theory, you could deploy these contracts to any chain that you want. For each of Avalanche and Moonbeam, we've deployed an ERC721 demo contract, the code for which was here. And we've also minted a token that would natively exist on Avalanche, right? And you see here, there's some note about metadata that that we're tying that to, which I've pre-populated within IPFS myself, right? And here's the URL for that metadata, which links to an actual image that we're going to be using for this NFT token transfer demo. And then you see that we deployed the actual NFT linker itself. And the addresses for the two contracts that we have are this and this respectively for Avalanche, and then this and this respectively for Moonbeam, right? So the next step is to actually get our UI running, which you can simply do by running.
I will pause you here just to mention one thing, that as you remember, when we just set up the dev environment, we've been deploying a thing called const address deployer. And by using const address deployer, then we are able to deploy our NFT linker to different chains. But as you can notice, it has the same address on those different chains.
Right. And as I was speaking through my explanation of the contracts earlier, I was struggling to find this very simplistic diagram that we put together. So basically, the contracts that we're dealing with are gateway contracts, which again act as those routers. And these are the two contracts that we just deployed in the deploy script that we ran just a moment ago. So here's that helps. So yeah, now let's go ahead and run our UI, which is just yarn dev. And this uses Next.js as a UI template, and we have for that Daisy UI as well, which we use to deal with our styling and our components, etc. So with that running, you see that that's running on port 3000. Let me just pull that up and drag it into my screen share here. All right, so this is really this is really kind of psychedelic, but what you're seeing here is this NFT that that we have hosted on IPFS, and linked to linked via our metadata to that NFT. You see that exists here on Avalanche, right? So what we're simply going to do is pass this NFT back and forth. And you do that by hitting the send button. After some time, you see that the NFT now exists on Moonbeam, and then you can send it back, toggle it back and forth. Right. So this is just an image of a car that we kind of borrowed online, but we do give them proper creds for all of that in the metadata for our for the image. But Kiryl's into cars, so he
That's right. That's right.
dictated this this as to be the example for us.
And just to recap what just happened behind the scenes with this kind of like send and NFT transfer. So on Avalanche chain, right, we have a contract called NFT linker, and then we have independent NFT contract that is basically represented by that car. And what happens is the owner of the NFT, which is car, call an NFT linker call and method called send NFT. And basically what it does, it transfers the original car NFT to that NFT linker, and that original NFT getting locked in that contract. So essentially we're locking the original NFT, and after this NFT linker sends a message across chain to another NFT linker saying that we just locked that NFT, so you're allowed to mint a copy of it. And then on the destination chain, NFT linker basically means the same NFT regarding the original one was locked. And when we're hitting send back from the Moonbeam to Avalanche, what happens, we're sending back the token that we just minted, and that token simply get burnt, basically it gets deleted, and on original chain, the original token get unlocked from the linker contract and sent to the destination address.
Yeah, and this is just our implementation of it. There are various permutations of what we could have done, but what Kiryl just described is exactly right? So when we did the toggle back and forth, what we were effectively doing was invoking this send NFT method from the source chain in question, right? So as we originated the transaction from Avalanche, what we actually did was we locked in this NFT that existed elsewhere, because remember when we deployed this, we also deployed this representative 721. What we did was we transferred the ownership of that NFT to this token contract as a sender. And then we invoked call contract, again, one of our building blocks in the GMP protocol, over to Moonbeam and instructed Moonbeam to actually mint this token, right? So you see that here. Here we're saying to send this native token from Avalanche, and the implementation of that basically invokes call contract. It generates some payload and some encoded bytecode for the payload that's passed into the call contract call. And then by the time we get to Moonbeam, now we're looking at the smart contract that's deployed on Moonbeam. This execute method down here does exactly that. It mints that token in question, and the owner of that is this NFT linker that we will have deployed on Moonbeam. And then the reverse operation goes if we're sending it back, right? So with Moonbeam as a source chain, what we're actually invoking is not send native token, but send minted token, right? And you see the code implementation for that is here. Again, invoking that same call contract building block. And by the time we get back to Avalanche, right, looking at this internal method, this internal execute method on Avalanche, what we're actually then doing is this block of code that transfers the NFT and unlocks it back on the source chain. So one helpful thing to show maybe is how we would invoke how we would invoke these methods from JavaScript. So what we actually run when we hit the send and send back buttons on our UI, right? So for that, the place where we implemented it is actually in our utils file. So here you see there's just kind of working through this. So there's some initial setup items that we have. And the method that we call is in sending the NFT from Avalanche to Moonbeam is this method called send NFT to dest, right? And then for the reverse, we actually invoke send NFT back. In theory, we could have combined these two blocks of code, but we thought it was helpful to show it this way because of the different parameters that you would pass into the method invocation of send NFT, given where the source, given where the NFT lives at any given point in time.
That's all right. Canh, do you want to elaborate a little bit more on the gas service, gas receiver, and the way it's used in the contract, and how you also invoke a SDK method to give it the right amount?
Yeah, sure. So going back to this linker example, right? Well, actually, I think a better way of kind of describing it is to go back to this diagram. So these NFT linkers, as we mentioned at the start, are of the form Axelar executable, right? So when we initiated the send NFT method here and had that message get to Moonbeam, the execute method doesn't automatically get executed, right? It has to manually get invoked by someone. And the process is actually one where you, just starting from the top, you invoke a message on our gateway. It then goes through our network. And then the receiving gateway on the Moonbeam side sees that transaction that comes in, and it does what's called lazily approves it, right? But it doesn't actually execute the method on the transaction on the NFT linker right at the start. So what we've created as a service on top of the Axelar network is one where a user can actually pay some amount of predetermined gas in the form of either the native token of Avalanche or native AVAX or a short list of ERC20s that we support. Basically, it's a separate gas receiver contract, which you can pay upfront in your single click, right? When you initiated that transaction. And we actually have a series of services that sit on top of our network that monitor the fact that you will have paid that paid for the execution of that transaction on the destination chain. And when it gets here, those microservices will see that that's been paid and actually execute that transaction for you, right? And it doesn't that execution doesn't have to be us. It could be anyone. If you decide to not pay the gas receiver, the transaction will arrive on the Moonbeam side, and you could then execute it manually yourself. And there are some services that there's some services that you can look at to trigger that execution yourself. But back to the point, if we go back to this JavaScript file, you see that for both send NFT back as well as send NFT, there's this method called get gas fee, right? So we actually expose through a JavaScript software development kit, a method that actually estimates for you what that gas cost or what that gas fee has to be, right? So if you're paying for the execution of a method on Moonbeam that would get executed using Glimmer on Moonbeam, and you decide to pay for that transaction in AVAX, that SDK service does the translation of currencies for you, given where current day prices are. So you get that gas estimation, and then you pay that gas receiver that amount of funds, which would then trigger the services that we mentioned before.
That's right. So basically, the Axelar network on its core is providing us with the security and relaying of the message, but Axelar core doesn't execute the message because of the gas cost. So for example, if transaction reverts or transaction might take a lot of gas, we cannot just execute every transaction across chain automatically. So instead, Axelar message relays the transaction, and the cross-chain transaction gets approved on the destination chain. And what the Axelar executable contract does, before anything gets executed with execute method, Axelar executable contract is actually validating with the gateway if such a call was approved by the network. And what happens on the source chain, before you call in the gateway and call contract cross chain, before that you pay gas, and then you call this method. And when the method arrives on the destination chain, because you already have paid for the cross-chain gas, our microservices can pick that up. And if you have paid enough amount of gas, our microservices automatically going to execute this transaction for you. So essentially, even if it's under the hood, it's like more of a two-step process, because we have built the microservice infrastructure on top of our protocol. For user, it's just a seamless one-click experience. And there is no compromise in security. And also, as Canh already mentioned, it doesn't have to be our microservice that relays the transaction. Basically, different services, different applications can have their own relaying services and not rely on ours. So it is absolutely open for anybody to participate in that protocol.
Yep. So the next thing that we would have liked to show you was this demo running in Testnet as well. As it happens, our testnet is going through a network upgrade at the moment that's expected to be completed actually momentarily. So we can't right this minute actually demonstrate the testnet transaction for you, but it's not going to be really any different from what we kind of walked through just now, right? So the way we have this repo set up, though, if it were the case that we were able to run this in testnet, would just require a simple parameter change in our environment variables, right? So let me go ahead and stop this. And the only change in going from local to testnet would be flipping the word local to testnet here, right? What you would then have is you would then have to make sure that your contracts are built and deployed, or rather built locally, but also deployed on the test networks of your choosing as well, using the same commands that we had run right at the start of this session. So again, it would be after you will have changed that environment variable, it would be the same yarn contracts deploy script, which would actually take your contracts and deploy it to Avalanche and Moonbeam in our example, right? One thing to note is because this key that we have is a public one, anyone can use it. So you just want to make sure that it has enough funds. So kind of an open call and invitation or plea for help to make sure that these accounts are properly funded. You can actually check the balances of this account, but I think there's a script that we have in the root directory. It's just a simple node script. Oh, something just happened here.
You probably don't have it in the env variable in the root level. So maybe you need to provide the address that you're checking.
Oh, you know what? I didn't install. Yeah, I didn't install my dependencies at the root level. It's yelling me about that. But basically, this command here will say, hey, for this key that you will have used, here are what your balances are in your deployer key. So if you deploy it and it works, great. But if there aren't enough funds in it, obviously you want to make sure that it's properly funded. But we provided that. I think it's a convenience for you to kind of get you off the ground, get you running off the ground as quickly as possible with development.
That's right. And yeah, there will be not much difference in the way it will work on the testnet comparing to the local environment. So the only kind of blocker for today is we actually upgrading our testnet and our services and microservices. So transaction will not get relayed at this moment. But rather than that, it will be exactly the same. So you will call the method on the source chain for the NFT linker that in order will call a method at the gateway, and then our Axelar network will relay that contract call approval to the destination chain gateway, and then our microservices will call NFT linker on the destination chain that will validate the approval with the gateway and then perform all the execution.
Yeah, that said though, I was trying to pull up a separate screen of where the I did this transaction in Testnet earlier today. And just to pull this into view, this is a view of our block scanner. So in testnet, it would just be testnet.axelarscan.io. And then for mainnet, obviously, it would just be axelarscan.io. But all of any transaction that you trigger via GMP is indexed and searchable here, right? And it's keyed by the transaction hash that is initiated on the source chain from the contract that you deployed. So from the NFT linker that you deployed on the source chain, right? So the steps that Kiryl just mentioned are seen here visually, and also could be helpful to look at as you're debugging the transaction as it goes through a network, right? So there are 4 steps to it. It's contract call, gas paid, call approved on the destination chain, and then ultimately execute on the destination chain. So if there are any issues that come up, I think our block scanner does a good job at showing you where any given transaction that you initiate gets stuck and helps you debug along the way. So a helpful tool to have as you guys are developing using our network.
That is absolutely right.
So yeah, that's all we wanted to show. Again, play around with the repo, and I think it should be. It is a bunch of code, but I think we've abstracted it into scripts that I think are easy to run. If you guys have any issues with that, feel free to do an open pull request back into the repo, because we don't purport that it's perfect by any means. But also, if you have any questions, feel free to post them in the chat, and we can address them as well.
That's right. I think now will be a good time, guys. If you have any questions, please post them in the chat and we will try to answer all of them. So,
All right, well, seeing none, I think we can call it a day. If there are any follow-up questions that come up, I'm Canh, and that's Kiryl. You can find us on Discord. We're, I think, fairly responsive and can kind of deal with any issues or questions that come up asynchronously.
that's right. So thank you everyone for joining today and listening to these learn sessions. Hopefully that's going to be very helpful for us, for you guys to get it off the ground. If you have any ideas of cross-chain NFT projects, this amount of code should be definitely enough to give you some starting points and be able to move your NFTs cross chains and develop new kind of applications. All right, so I think Roman is trying to ask a question. Is question coming or not? The only I see is such a question, but there is no question. Where is it?
When can I use gas service contract for BNB chain? I assume you're referring to mainnet. Yeah, we don't have our gas service contract deployed to mainnet on BNB, but we will soon after our upcoming mainnet upgrade, which is expected to happen within the next week or so.
That's right. So basically, we support currently we support BNB chain only in testnet environment, and mainnet support for BNB will come with it within a few weeks, and then we're also going to have a gas service contract there as well.
Correct.
All right, awesome. So I believe this all the questions that we got. Again, thank you everyone, guys, and we'll talk to you next time.
Thank you. Take care.